So I'm going to talk about some Marx generator work that my student Cameron, who couldn't be here today, did as part of his PhD dissertation. This was only a part of it. I'll start first by talking about the pulse power principle for anybody who's not familiar with that. But pulse power is an electrical technique where you store energy up very slowly and then you release it very quickly. And in order to do this, there's quite a large number of specialized techniques that we use. Here's the shows the principle using the Sandia Z machine. In this schematic shown on top, a Marx bank charges over a very long period, over a microsecond, with an energy of 11.4 megajoules. As it goes through a series of capacitive compression techniques, it ultimately produces X-rays with very short duration pulse. The efficiency is 15%. This is a very large machine. But these techniques, you see, are very specialized and show some, they're only used in very special applications. So my favorite definition of pulse power is for special power conditioning. And part of this, I like it to reflect that there's always a load and everything we're doing is a custom design specifically for that load. The Marx bank that we're going to talk about today is particularly useful for the energy storage stage. That's where you take a DC charge and you convert it into a pulsed, a high voltage, which kind of on the order of microseconds. Everything in pulse power is variable. So the same techniques are used over widely different time domains. The energy storage in the Marx bank in particular is used for voltage multiplication. And these have been used for a number of years. These are a number of machines from Sandia, where I used to work, as well as Trestle. So these are very different applications. Saturn is a high current driver. Z machine, it makes X-rays to test nuclear weapons. Hermes is an ionizing radiating simulator, and Trestle was a high power electromagnetic facility. So all these use the same basic technology, the same high voltage techniques to drive the simulation technologies, all for very different purposes, and the loads are very, very different. Now, when we look across sort of the history of high voltage and then pulse power, we sort of see some trends and we can try to classify things. So the earliest period is what I think of as the age of high voltage technology. And that's where there was a lot of work being done, people like Paschen, Erwin Marx, Peak, mostly for the power grid, where they were learning to make the high voltage and learning all the fun stuff that can happen with high voltage, including corona and its uses. Right after World War II, we really entered the nuclear age, and that really ushered in a very different focus on high voltage, where we're looking a lot at simulation technologies. So that went everywhere from big machines to replicate some portions of the nuclear physics, but it also did very high electric fields like for electromagnetic pulse that we've heard quite a bit about today. After the Cold War ended in the 1990s, we really started to enter a different age, what I call the age of applications, where we're taking the techniques of pulse power and applying them in yet more ways. And in fact, they're really in the early 2000s, there was an explosion of commercial applications, industrial applications. And that's really in addition to the businesses that are out there for simulation. You'll see at the bottom I put, there's a line about the pursuit of fusion. That's sort of a joke, since fusion is always 50, yet 50 more years away. So the challenge now for pulse power, particularly for high power electromagnetics, is that we have this dream where we can have very high powers in very small packages. We can use these for protection and in any number of ways, medical applications, agriculture, and it all goes back to getting these into very small sources and making it safe, making it usable for a consumer. The reality, however, is that it's really hard to make these high powers very small. So certainly in the laboratory, we don't try very hard. This is Professor Shamanoglu's laboratory, and this is just used to illustrate that, you know, he's studying the source end, so his pulse power is very big. But in order to take that amount of pulse power to drive and put it in a very small package takes some really very specialized techniques. So Marx generators are key elements. I mean, they're absolutely essential. In fact, they're the most ubiquitous high voltage multiplier technology. And one of the problems is they come in all shapes and sizes. So they're also custom for every application. So for instance, in this picture in the lower right hand, there's a Marx bank that's driving a Marx bank. And that just shows Marx banks on 2 different scales used for 2 totally different purposes. The one in the middle is one that's in my laboratory that I'll be talking about today. That's a very low energy Marx. It's fairly fast, kind of in the nanosecond range. But the same technology that drives the very, very high voltages seen in that Marx bank on the left from Dresden, the physics and the erection processes are all the same. So here's the simple picture. Now we've all, anybody who has a Marx bank is given a lab tour and explained a Marx bank operates by charging capacitors in parallel and discharging them in series through spark gap switches or other switches. This is a quote taken from the really excellent paper of Morrison and Smith, where first they note that the voltage that's being put on the load is NV0, and that actually is not correct. Anybody interested, Mark? I recommend the Morrison and Smith paper. It's a really nice analytical paper looking at the erection process back when the technology was going from very, very large Marx banks to ones that were smaller and much higher in density. So to start analyzing a Marx circuit, we actually have 3 different circuits, and it's often convenient to separate them. The first is the charge circuit. So the point is, for the simple picture is, we talk about this picture all the time, and it's really not true, and we sort of already know it's not true, but it's very easy to forget. The other part is that when we talk about the Marx bank erection process, we assume that once the first gap fires, all of that voltage is relayed to the second gap, while all the other stages are kept at ground potential. So this means that the second stage is highly overvolted and the rest are not overvolted. We're specifically interested in the erection process. The circuits are separable, that the charge circuit and the discharge circuit are both very important, but the erection process is the one that's most critical to its operation. One thing, that this actually uses the discharge circuit, so we can easily make an equivalent circuit by reducing the Marx equivalent to a capacitor and series with an inductor as a very simple model. And when we put say a capacitive load on it, we can analytically solve this, and we look at the a voltage multiplication waveform. And what we see is two things. First, the if we look at the capacitive ratio, the ratio of C2 to Cm, that is the load capacitance to the Marx capacitance, we see our regime, our important regimes of circuits. One is the resonance circuit, which gives us the 1 minus cosine waveform, where we'll get about equivalent voltages. So that's where we're transferring a voltage from one capacitor to another, and we can do that very efficiently. The other side gets as a peaking circuit, where the capacitance, the load capacitance C2 is much less than the Marx capacitance, and the voltage can get much higher. What we see here, though, is that the voltage is not equal to the open circuit voltage. In fact, it depends heavily on the load capacitance. Okay, now we can make an equivalent diagram for the resistive case if we choose. So Cameron and I were working for his master's degree on an application, and we were using this. In fact, we were using the change in the Marx output waveform as a detection mechanism. So that is when the load changed, we could see that and react accordingly. So we were doing an experiment where we had what we called a reconfigurable Marx. It was a Marx that had the stages arranged so that we could independently test voltage and power or energy. And from that, we used that to do a scan. We derived some Marx equivalent parameters, and we built a Marx that's shown there in the bottom. They call it the blue Marx. And the blue Marx was interesting because in the first iteration, it had a metallic cylinder on it. And we took it off because we were having a lot of trouble with breakdown. We just couldn't get it close enough without breaking down at the pretty high voltages. It was about a 400 kilovolt Marx. And so instead we changed it to a plastic housing. And when we did that, it absolutely refused to work. It would not trigger. In fact, the first stage would trigger, and then no other voltage will come out. So in inquiring from expertise, what I found was this is actually very common to see in low energy Marx banks. They tend to have very poor triggering ranges, inconsistent erection, large pre-pulse. And the biggest problem with that is that what this means is just like in this example, every time we know exactly what kind of a Marx that we want, and we still can't get there. So what we have to do is we have to build it and then go back and analyze it and then fix it. And a retrofit fix is never as good as designing it right the first time. Yes. So the motivation for starting this specific project, that project is long over, really harks back to Carl. I'd like to pay homage. Carl really was a big proponent of the meandering research project, that you take a look at something, and he used to say, well, as long as it's right what you wrote down, sooner or later it'll prove useful. You don't always have to know where you need to go. This is particularly important for pulse power. So on the left is a quote by Jerry Rowein, who I worked with during the JOLT project. And he said, I was a young engineer at the time, and he said, pulse power is black magic, because if it were science, anybody could do it. And that's really true. I use this quote often with students, partially because we get a lot of surprises with these very high fields. But ultimately, the motivation for this project was to really be able to design a priori a high power electromagnetic apparatus that is, if we need a Marx bank, we should be able to sit down and, you know, maybe not do it exactly, but kind of get a device that's maybe within 10 or 20% of where we want to be. Not that we have to double the time allotted to make the high voltage equipment, because we know something's going to go wrong, i.e. the black magic. So how do we get the black magic and turn this into engineering and science? So we'll start with the conventional description of a Marx. Again, there's an expectation that once the spark gap S1 goes, that voltage is all transferred to the second stage. The rest of the stages are held at ground. It turns out when you look at that assumption, there is zero reason why that should be true. And in fact, we did do, well, Cameron did a detailed analysis. And what he found was after the first gap goes, the voltage actually redistributes along the Marx erection path. So that means depending on a lot of on the straight capacitance, it depends on where the voltage is going to go. And in this example, because the load is resistive, most of the voltage goes onto the fourth switch, because it's actually tied to ground through the load resistor. So what really happens is, so this is a combination of analytical investigation coupled with modeling. PSpice, even for relatively simple circuits like this, is really powerful. We also used a spark gap model that we developed and validated with experimental data. So we're very confident about these. So what this plot shows is that indeed the last stage fires first. This is something that pulse power engineers will be like, oh, I've seen that again and again, and it was always so mysterious. And what we see under these circumstances is that it almost has to go last. Now, because everything is so custom, this doesn't happen in every Marx bank, but it happens enough that it's notable. So the types of straight capacitance that we're going to look at, so we sort of looked at sort of a canonical Marx bank with reasonable parameters. So the straight capacitance are first the gap capacitance, the straight to ground capacitance, that is from the capacitance between the capacitive stages to the ground, wherever that is. The interstage, that's stage to stage capacitance, and then the load capacitance. Part of what makes all of these very real is that you'll have a capacitance for any 2 points with a voltage on it that is separated in space. So we always have a lot of straight capacitance around. We need to find out what's important. So we started first by looking at the gap capacitance. So it turns out that the gap capacitance, that little bit of capacitance for the gap, and the order of magnitude of that gap capacitance is only going to be, you know, a few picofarad. It's possible it could be more, but it's certainly not huge. But what this straight capacitance does is it redistributes by forming a voltage divider for the erecting Marx. So when you have, what the implication of this is, for very large N, you'll have less over voltage on every stage. There's also the stage to ground capacitance. This turns out is a vital component for this, at least for this class of Marx, because what it does is it forces most of the overvolt to go on to the second stage, which means that you're now going to erect in the sequential form that you want for maximum energy transfer. We see in these figures that we now have sequential erection. We go S1, S2, S3, S4 onto the load, and the output or the overvoltage on S2 depends on the ratio of the straight capacitance to the gap capacitance. So we're actually acknowledging that we always have a gap capacitance. In fact, we need a gap capacitance. The next is the interstage capacitance. This can be very variable within Marx banks. It can be very small, relatively negligent, or it can dominate. And here we find that we can reduce this easily by adjacent stage coupling, that is kind of coupling to every other stage. The problem is that's really hard to do on compact geometries. So to go back to the, so how does this manifest itself? This is, so we've been working on this actually for a couple of years. We were in the process of repairing a Marx, so we decided to take it out of its can, so it's only its naked backbone, if you will. And we fired it into what's essentially an open circuit, into the North Star probe shown there. And one of the things we see is that the quantity N times V charge is 200 kV, but our load voltage is only 160 kV. That is actually the effect of the straight capacitance and what is known. It's going to reduce that voltage. So this, this is something. The importance of straight capacitance is certainly known. What is it's maybe underappreciated. But the bigger problem is, how can we know this during the design phase? When you're building a system, the amount of voltage or the amount of current you need in your prime power is an important quantity. And right now we're sort of guessing what it's going to be. So what that means is we have to over design, which is going to make our systems bigger and more inefficient. The Marx that we're specifically interested in right now is what's known as a wave erection Marx, or we call it a Platz Mark. It was Dave Platz in the 80s wrote a series of papers that were just really exciting. He was the first to start making these sort of little self-contained, really cute low energy Marxes. Some are shown, mechanical schematics are shown there, where they're low energy. They're just maybe 2 nanofarads per stage, with these spherical spark gaps. You can make them in house, and they can work very well. They can be also very fast. Kekes did a beautiful job of illustrating that, where he did us, hundreds of picosecond rise time in 200 kV. So in the Platz Marx, the straight capacitance is really very important. It's especially important because you're trying to use that straight capacitance to make every stage a peaking capacitor, so that at every stage you're going to peak up your voltage. So you think, well, you probably get more voltage out, turns out you don't. And Dave Platz did this by using a metal cylinder close into the Marx erection. So there's some design issues there with, as the Marx erects, you tend to have a breakdown problem, but you can make them work very well. One thing we found, so this goes to the wide variety of Marx architectures that are out there. So in general, you can make the interstage capacitance very small. It can also become surprisingly big. So for instance, say you have some specialty capacitors. So there's a diagram shown there, but the plates are big, so you have a lot of them. That tends to increase your interstage capacitance. And the real problem is it's in parallel with the gap capacitance effectively increasing. For the purposes here, we're just going to call that CG. And so we already, we know when we go back and look at the stage capacitance, we find that really it's not the stage capacitance that's important, it's the ratio of the stage capacitance to the ground capacitance. So what this allows us to do is parameterize, and we can do that. So we know for good erection, we need we need to optimize this ratio CS to CG. This here is a study on what's the reasonable numbers for CS to CG that you can get just through geometry. So one thing we tried was, what if you took the plates and you cut holes in it so that, you know, you would have less capacitance between them. It turns out that's negligible. It's really not worth the effort. Increasing the radial gap can be very good. But again, because it's the ratio, this allows us to look for, at the stage to stage gap, the capacitive ratio is a function of stage to stage gap for a number of radial gaps. And we find that, you know, if you need ratios on the order of 5 or less, you can do this through geometry. That's a very easy, passive way to do that. But the problem is, if you have a lot of interstage capacitance, your gap capacitance is going to go up, and this won't work. So in order to make that kind of a Marx erect, we'll put in something called a coupling capacitor. And what that is, it's a small lumped element capacitor that goes between the second stage and ground. And what it's there for is to increase this ratio of CS to CG. And this is shown to be very important, very reasonable. This, in fact, is how we fixed our blue marks. And this comes to this manifests as a limitation in the voltage operating range. So here are 2 marks. One is from the literature, this one on the right, from Dahlgren. And so they used they used coupling capacitors for 3 different stages in varying amounts. We only used 1. But you see, they can charge to higher voltages, which is great. It get a little bit more range. So they can go down to about 75% of self-break. These tend to be a little bit nonlinear. And our Marx does 85% of the self-break voltage. This is really not a very good range. And what this means sort of in the field is that you have to balance, you have only a very small margin between a pre-fire, which is close to your self-break curve, and a no-fire, which is at your minimum trigger. So what this means is you have to keep everything very, in order to have it work, it has to be very tightly controlled. So here's our blue marks with the coupling capacitor. This has a huge 1,000 picofarads capacitor coupling the second stage to ground. But what this does is, because this was built in-house, it allowed us to first analyze the first version where it was in the metallic can, and that showed that the capacitive ratio was about 3, and it erected, it worked fine. When we took off that metallic can, it decreased that ratio to about 0.3 and wouldn't erect at all. When we put this coupling capacitor in it, it increased it to about 175, and we see the slope on the voltage range is wide, and it's wider for higher pressures, which is good. And this was fairly easy, but that only happened because of the parameters that we were interested in. So our limitation on the stage to ground capacitor is that so the question here is, well, okay, well, we know we can make it kind of small. What if we want to make it big? Is bigger better? Is bigger always better? So it turns out that when we look at even just the one stage, because this is a peaking circuit, we already know that a peaking circuit is inefficient. So we can expect this to be inefficient. And we know we're going to get voltage loss. So the question is, how much voltage loss can we calculate that? Can we learn to expect it? So we started doing circuit analysis. This was certainly started by hand. And we had these very large equations. So what we did was we took one stage and had it erect and did the circuit analysis, fired another switch, did the circuit analysis again, and then tries to close the form. So we had some very large equations. So it turns out we could only solve this. We couldn't close the form for the very general case, but we use loops and we can get good numbers. One of the things, so there's another case where we keep the stage to, this is a different ratio, where the ratio is this straight capacitance to ground relative to the stage capacitance. We did close the form, but what's interesting here is in that top equation, we can see that as the number of stages increases, the voltage will decrease. And that's very troublesome. And in fact, the Marx that we have is a 25 stage, and it could be too much. So that was very interesting. So here's a comparison of the exact solution to our closed form, our approximate solutions. And so we can see, as we expected, that at low ratios of straight up Marx capacitance, the solutions converge. As that ratio gets bigger, you don't lose as much voltage as you would in the other case. Not unexpected. So this allows us then to look at it from a different point of view. So this is a surface plot of the exact solution, where again it shows that so for just a few stages, we used 5 as a reasonable number. We'll have very low loss, and that's a perfectly good solution. But as you get up, as you increase the number of stages, you begin to lose more and more voltage. That particularly gets bad with when that capacitive ratio increases.
Sorry, if we have 1 more minute left.
Okay, well, I have 1 more slide, so.
Sure.
So this is a different way of looking. So this is sort of from a more design point of view, that how much voltage can I afford to lose? And the section is white. In white is where you would, for every stage that you add, you would only get 20% more voltage. So it means that you want to stay out of that. So this gives us kind of a handle, an estimate of the performance that we can get. And these are some measurements. This shows for our Marx, when we took it out of the tube, we knew we lost some voltage. Our NV0 is 200. The peak here is 160. When we put it in the can, we add all that straight capacitance back in. That is only 45%. So we lose even more voltage. So not surprising. And that 45% extracts the overshoot that we see here. So in conclusion, we are marching on our way to making Marx banks more designable and ultimately more reliable. And we have a paper coming out on this soon. Thanks.
Thank you so much. Thank you so much for the presentation, Professor. Guess we can take one question from Dr. Nicholas. When you design compact transportable pulsars, you end up increasing significantly the stray capacitance to ground.
Mm-hmm.
These stray capacitances may start to be comparable with the stage capacitances or the peaking capacitance and become an issue.
Mm-hmm.
What do you suggest to overcome this trade-off? Briefly, if you can understand.
Well, one of the things that we're finding is that the Marx is always it's parametrizable because it's always a ratio of capacitance. So, so the straight capacitance to ground should not be anywhere near equal to the stage capacitance. Because you'll have a crazy amount of loss. And that probably means you need to put in some additional, you need to strategically put in some capacitance to fix that.
Thank you so much again. It's a pleasure.
Thanks.